Okay, let's look at our impulse momentum theorem, or basically Newton's second law, written this way. Our change in momentum is equal to F net, um, F net as a vector delta t. Okay, or if it's not constant force, we just integrate F net with a small delta t. Okay. And as any vector is, I'd have to separate this out for x, y, or z, or r, or s, or just whatever component I'm talking about. Okay, we're going to now kind of look at and introduce conservation of momentum. Again, as I mentioned in a previous video, one of the most important conservation laws there are, and so broadly applicable. And we're going to see just how broadly it is, or introduce how broadly applicable it is in this video. So let's take a look at like two objects that are colliding. Okay, two objects are colliding. Okay, and I want to find out we'll call this 1, call this 2. And I want to find out what is the change in momentum of object 1. So that'd be delta P1. Well, it would depend on, let's go ahead and do the full integral form, of the net force on 1, which is from 2. So this would be 2 on 1 times the dt, and go from the initial to final. And if it's like 2 billiard balls hitting, that dt is super small. But the force would be pretty big. If you stuck your finger in between it when they're about to collide, that'd hurt. Okay, so that would be a pretty big value, but a small time. Well, I could find the delta p of that one. Well, what if I want to look at delta p of the other one? Okay, well, I'd have to do the same thing, only this would be f1 on 2 delta t, right? But we know by Newton's third law that f1 on 2 is the same thing as negative f2 on 1. Okay. Newton's third law says that two interacting objects have equal and opposite forces. Okay, but this is just the negative of this one. So that says delta P2 vector equals negative delta P1. Right? And this looks an awful lot like conservation of energy, where we have a change in one thing gets transferred into a change in another thing. Right? But in this case, they're the same type of thing, momentum, as opposed to potential energy versus kinetic energy. Right? But what if I take this over on the other side? I have delta P1 plus delta P2, so add delta P1 to the other side. That gives 0. If I choose for my system both balls, okay, if I choose for my system both balls, such that the forces are just interactions between the objects inside my system, that means there's no external forces. Okay, I could write that as net external, add a little external there. And that's 0 because I've chosen both of them to be in my system. And it says that the momentum of my system is conserved. It says delta P system is 0. And it's a vector. Notice this is a vector, which means delta Px system is 0, delta Py system is 0. All components of this are changes are 0 separately. So this is actually 3 equations right here for 3 dimensions. This is conservation of momentum. And it's true whenever we can choose a system such that all the interactions are inside our system. We just have to then catalog all the momentums of each piece of our system. Sometimes this is really, really nice to write this way. And for every component, so I'll write the x, it'd be P1 x initial plus P2 x initial equals P1 x final plus P2 x final. And I'd have the same thing for y and the same thing for z. Okay, to start, we'll just focus on one dimension, but notice you just do the same thing for every other dimension. All right, and so if I know how my particles started, let's say I could see how they're moving together, and then I could, if I can measure one of their final speeds, I can automatically, using conservation of momentum, find the other final speed. Or basically, I have these four variables. If I know 3 of them, I can find the 4th. All right. Now, this can be applied in cases where you might say, well, there are external forces. Okay, so if I rewrite this and say delta P system is equal to F net external. Okay. Sorry, I didn't finish writing this. This should be delta T here, or dt here. Okay. I'll put this inside an integral and have a little dt. Okay. What if these two balls are thrown in the air and they hit each other while they're in the air? So I've thrown it up, and I've thrown this one up, and they hit in the air. Well, there's a force of gravity that's not zero. It's not small. And so it's acting on those. But the time of collision is super, super small. When you throw two billiard balls up in the air, or two bouncy balls, the time that they're colliding is really, really small. And so this force of gravity, which would be an external force, though it's non-zero, it's multiplied by a teeny, 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 tiny value, which this quantity, this whole quantity, this impulse acting on the system, this external impulse, is super small compared to the internal forces, such that we could neglect it or ignore it. And so that is an approximation, it's called the impulse approximation, where when during things like collisions or explosions, basically whenever the time involved for the event is super small, then this quantity is sufficiently small to ignore it and say that momentum is conserved for the system. So this is even true for things like this, where the balls are colliding in the air, okay, where gravity is non-zero. So this is conservation momentum. Basically, delta P of a system is zero. It's true for all or each component separately, and it's even true when you have significant external forces, as long as the interaction's fairly small. I'm going to even do an example where even if the time period's not terribly small, but for other certain circumstances, this is still true. So this is true under so many different conditions.